Okay, so good morning. I want to give you a brief update of this proposal of building a underground laboratory. So let me go quickly into the details. As you know, the idea is to use the opportunity that there was going to be a tunnel across the Andes. We want to use that tunnel to build a scientific laboratory, which would be the first one in Latin America and probably the first one in the southern hemisphere. So this is the content of the talk. I'll briefly talk about the tunnel and then the Andes proposal, including the design and little details of organization, then the support we need right now. So the tunnel. This came from an intention of connecting the east and the west coast of South America to have essentially access for Brazil and Argentina, the access to the Pacific. So there were several tunnels planned, and the mountains are rather high also, and so the passes usually are covered with snow during most of the year, so it would be an advantage even for the communication with the two countries to build these tunnels. There are three proposals of tunnels. The most advanced one, in terms of time, the earliest one, will be this one here in the north, which is the Túnel de Agua Negra. And then there are two other projects which are further in the future. The one here, Las Leñas, is still at the level of conversation. It's a similar tunnel to the one in the north. It's about 14 kilometers long. It's a bit lower altitude. This one is at around 4,000 meters above sea level. This is about 2,000 meters. And then there's a third proposal, which is the one that in Chile was spoken a lot because it's close to Santiago. And well, it's actually people in Santiago were speaking a lot about that. But it's a very long tunnel. It's like 50 kilometers long, so this probably will happen when our grandchildren are around. So right now we are focusing on the tunnel that would be built in the Paso de Agua Negra, which is in the region of Coquimbo in Chile and San Juan in Argentina, the province of San Juan. So this is another map here of the terrain. As you see, the two main cities close to the tunnel is La Serena, which is it's a beach resort, and a port, Coquimbo, in Chile, about 200 kilometers going up here, the mountain, 4,000 meters up. And then on Argentina is the city of San Juan, which is also around 200 kilometers, 250 kilometers. So. This, of course, presents a challenge, this distance, but it's part of the situation. This is a drawing of a cartoonist, an old cartoonist who actually passed away like 10 years ago. He was an Italian immigrant to Valparaiso, and he wrote every day a little cartoon for the main newspaper. And I found this one about passing from Chile to Argentina and vice versa. He was sensitive to that already. So, so this is the map of South America. This is a location about about 30 degrees south. La Serena is a beach resort. The Chilean side here is also the place where the first international telescopes were built. Cerro Tololo is around there, La Silla. And on the Argentinian side, you have the province of San Juan, in the city, very nice city. So the tunnel itself would be about 14 kilometers long, two tunnels, one going to Argentina, one going to Chile, two lanes each, separated about 100 meters, connected every 500 meters with, access tunnels, some of them for vehicles, some of them for pedestrians. The deepest point is pretty much near to the border. As you see, well, this is not a scale, but you can see that the mountain goes steeper on the Chilean side and then more flat on the Argentinian side. So means that the deepest point and the border is closer to the Chilean entrance. It's about 4 kilometers, and then the other 10 kilometers to the Argentinian side. This is a bit lower. This is at 3,600 meters above sea level. This is about 4,000 meters, so there's a slope here of about 2 or 3 degrees, which also has, this is important for the water to, to run down, for ventilation, also normal ventilation to go through easily, and also poses some problems of concern with the environment. Water that comes to that side, should be fulfilling some regulations, etc. So there's also an issue especially for Chile. So now the laboratory, the proposal, as you see here, is the map of the world. All the existing laboratories are in the north. Some are existing, some are being built. I think this is Jinping, which will be the deepest. And there is also a proposal in Australia, Stawell, which at some point we thought it was going to be built before Andes. Right now I think it's not so clear. Well, I already mentioned this. This was our first, design of 2 caverns, 2 horizontal caverns, and 1 large pit. So the basic idea is still around, but the design has changed a little bit. I will mention that. Here you have the attenuation of the muon flux to give an idea of where Andes would stand compared to the other laboratories. So you see it's comparable to Homestake in the United States, Baksan, Mont Blanc, Modan. Sudbury is deeper, and Jinping also will be deeper. But Kamiokande and Gran Sasso, they're not as deep. This picture here is signal to noise ratio for neutrinos of MeV kind of energy. So it's relevant for geoneutrinos, for example, or neutrinos with those kind of energies, maybe supernova neutrinos. And the place here, you should see the place in the crust of the southern hemisphere. We're far away from reactors, which is in some sense good. And now the scientific program. Well, obviously, large underground laboratory should have a program with neutrino physics, dark matter, and we also plan geoscience, biology, nuclear astrophysics. But the important thing here is to start working on some, science white paper. This is a very important issue that we should address here. So I won't go over the details. This is some work we had to do. Now the conceptual design of the lab was actually, it was the idea itself of the whole project is to have the underground cavities, then 2 support laboratories, one in Argentina, one in Chile. We have to decide still where the sites will be. Most likely La Serena will be one of them because of all the infrastructure of astronomy, which will help for the technology. And another one which should be closer to the laboratory we're proposing it to have it in Argentina, in the town of Rodeo. And then also we propose to have some sites by the portals of the tunnel. For people who are going to work there for like 8 hours or something, they come out. They don't have to travel 200 kilometers back to the city. They just simply stay there. This was one of our first drawings showing the kind of cavities we needed. But this changed after we asked Lombardi, which is the company who's building he's doing the engineering design of the tunnel itself. They also are experts on laboratory designs. So they did the first conceptual design after all the details that we gave them. And it came up something like this. This is one of the proposals. They have a different alternative depending on the orientation and the size of the laboratory. So they said, well, the tunnels, the access tunnels have to be much longer than we expected, so the cavities, for the stability of the rock, have to be more separated. So here you have the small, let's say, gallery, the cavern, and then the large one, and then the pit. And we propose some other things here, but this will change anyway. And here, what I wanted to show you is, this is the tunnel that goes from Chile to Argentina. This is from Argentina to Chile. The mountain is higher on the south, so it's more convenient to build the laboratory on this side than on the north side. Then there's also here, you see this tunnel in the middle is the ventilation gallery, which ends like around about 800 meters or something like that from the border on the Argentinian side. So there was an issue about where to place the laboratory, right at the border where it's apparently deeper, or close to the power station for the ventilation, which would be also easier in terms of ventilation for the laboratory, which is something very important. So those were some of the issues that came up, and also some issues about safety. Let me go back here. So you see, for example, this is a pit. So you have access. This is a pit of about 40 meters high, and you have access here from this tunnel. You have access to the top. The access to the bottom will be in the initial time when you're building something, and then you close it. Is here. So this road is going down to the bottom. So the point is, if you are somewhere around here and there's a fire here, you get trapped. So this is not safe. So we had to have some other, some modification of this. It was also considered. And another change was to include specialized galleries for geoscience. So the proposal was to build at the end of the gallery here, say, a tunnel of a smaller diameter, without ventilation or something. Will be just simply closed afterwards. So to enter this part here, you need some kind of equipment, but rather long. It's about like 200 meters or something. And so this was also something newer in the proposal, which we will hear soon. And here I'm showing you one of the other designs of a smaller kind of arrangement, more just perpendicular to the tunnel, but placed at the place where the ventilation power system is. So here is something that yes. Yes, this is about 50 meters long, about 20 meters diameter, more or less, 22 meters something. And this one's a bit shorter. The dimensions are, let me see. I think they're further advanced. Well, let's just look at them. See. So this is the main cavern. You see, this is the base is 21 meters by 23 meters high. And this is the second one, is about 14 meters high, 16 meters wide. This is the pit. It's 38 meters to the top and 30 meters diameter. So those are the main. Let me go back. Where was I? Here. So Xavier found this, and this stimulation, I suppose, with the data of the mountain, where would be the best place in terms of depth. So this is the place at the border, and this is the place where the ventilation power plant is. And the blue is shallower, and the red is deeper. So from the point of view of omnidirectional depth, this is a bit better than this site here. But the figures are like around, let's see, I don't know if I can read here. This is like 1,600 meters. And here is like 14 or 1,500 meters. So So it's like 100 meters difference in depth. And for the neutrino, for the muon flux, it's, well, also you see here, they are rather comparable. This is a little bit better than that. Still, that's what we have. So we have to ponder on that. And with all the requirements, the new conceptual design has this shape here. And you see we have eliminated a smaller pit that we had there originally. This is a large cavern. This is a secondary cavern, which is partitioned in different sections. This is a large pit that is connected now in different ways for safety. This is it's not to scale, but this is the geoscience tunnel. And there's some biology lab here, some clean rooms, technical rooms, etc. Some place for safety also, which I don't find, where is it? Well, this is a room for treatment of water. So you enter the tunnel here, and the laboratory has a door here. You enter here, and then the vehicles go out, except for the ones who are allowed to enter the laboratory itself. This is also a room that I don't think this is the correct emplacement. Most likely will be in like perpendicular here. Is a isolated room for doing let's say nuclear astrophysics. So you may have sources of radiation there that you voluntarily put there. So you want to be isolated from the rest of the experiments. And we also saw that already. So let me skip this. This is the main access tunnel. You can see that you can put two vehicles side by side. Well, here the data, you don't want to read this anyway right now. And then there are the support labs. Also, we plan to have the support labs with some interactive museum, because we want to do a lot of outreach. This is important for us. In terms of organization, well, this is something we have to discuss. There, at least the main idea, basic idea, is to have a consortium, international consortium, that will be like the consortium that will manage everything about the tunnel, and it will be, empowered by the country, the member of the country members of this laboratory, and they will make all the decisions. And there is a model of organization in Sesame, which is also international, and I think it's, well, something we'll hear on this workshop. And now we are right now at the level in which the conceptual design is already done, and now we are in the basic engineering and the documentation for the call for tender. This is something that is in process. Argentina already committed to pay for that. Chile is still wondering, which is something we have to address. And these are the coordinators. And summary, we have some issues that are pending. As Xavier was saying, we need some signature and commitment of the countries, especially in Chile. There's not official, I mean, we need a real signature that the laboratory will be placed there, and with that, the entity that takes care of the whole project of the tunnel, which is called EBITAN, Entidad Binacional Túnel Agua Negra, they will, put Andes in the project of the tunnel when the countries, they both agree on that. So, well, and as I said, we also need to work on some real science proposal, some white paper, and it would be good to have some letters of, some more important letters of support of the scientific community and scientific organizations, international, that get directly to the countries, Chile and Argentina. So, thank you.
Questions, comments?
No questions?
I think I saw in your the design that there is just outside. When you go outside of the lab, there should be a place to cross the road, right? So I was asking whether there is an access to both sides of the.
Yes. There.
And
So
this is only for the laboratory use, so people cannot use this generally, or this is for the general public if they want to U-turn or whatever.
Here?
No, when you go outside.
Here.
Yeah, let's say you want to go back to Chile or to Argentina, so
Well,
you can cross.
No, I mean, yeah, these belong to the tunnel, and it doesn't need to do the lab. This belongs to the tunnel. The design of the tunnel has these connections. This is for, I think this is for pedestrians, and this is for also vehicles. But a normal vehicle will not be able to do that. It's only for an emergency. I mean, you're coming to the laboratory to work here. You enter with your vehicle. You park here, and then you work, and then you leave here, and then you have to go to Argentina. You will be most welcome on the other side, and then you come back here if you want to go to Chile or stay in Argentina.
So that's like half an hour drive if you need to come back.
Probably. Oh, well, yes. 10 minutes for me. Yeah. Yes. Yes.
So I'm just saying this needs to be thought if there is an emergency and somebody is staying on the Argentinian side, for example, then it takes him half an hour to come to the lab.
Sure.
Half an hour is quite a lot in terms of an emergency of an experiment. So I don't know. I mean, I'm just saying this needs to be thought.
Well,
You mentioned already that the design has some segmented portions of the lab. So if there is a fire event in some of the regions, then you can be isolated.
I was referring to emergency in an experiment.
An
Let's say the
yes.
cryogenic system
Yeah.
breaks or whatever.
Well, the situation
not
is
ecological.
similar to what, for example, Modan has also a tunnel about that size, and you also get to that kind of time scale to do that. Well, if you would have some, people watching for some emergency action, then the most convenient thing would be to have people in the Chilean portal, to be there, stationed, so that they will take, 4 kilometers is not so far away.
Yeah, I'm saying because this is kind of a nuisance that happened to us in Gran Sasso because we sleep on well, for here it's the Argentinian side.
Right.
So if there is an emergency, it takes roughly half an hour to arrive. And this is in terms if you woke up really fast and you heard the alarm immediately and there is no problem. So, I mean, I'm just commenting that this is something you might want to consider or think about.
Okay. What's the distance from the entrances of the tunnel to Gran Sasso?
I don't fully remember, but I think it's roughly 10 to 15 kilometers.
Okay. Mm-hmm. All right.
It's comparable.
So
This is why I'm commenting on this because we encountered this. It's doable.
I mean, yes,
it's doable, of course. And what can you do?
Yeah.
Exactly. But
you have to consider that. Yes.
If you are building something new, then and you already know about this, then you might want to consider somehow this.
Yes. Very good. Mm-hmm.
See as a different from the Mont Blanc, the laboratory is somehow shifted to the south of the tunnel. Likely, I mean, the most risky region are the tunnels themselves, not the laboratory.
I'm just referring science-wise.
Yeah, no, he's talking about the experiment. You have to go and run and
I'm a
fix
shifter, I work on the experiment, I'm there, I need to guard the experiment. I wake up in the middle of the night, there is an alarm. Something, I don't know, there is a power break, cryogenic failed, I don't know. Something happened, I need to reach fast.
Yes. So probably for that we have to consider that the portal on the Chilean side should have some good space to stay there. It's also a bit lower in altitude, so it's probably more comfortable. But it's a good point. Yeah.
Thank you.
Yeah, there are worse places if you are in Snow Lab, for example, and you have to go down. It's it's more difficult to access. But yeah, that's a good point. So we had planned to have this area where you can stay to be close, which are these offices at the portals. Portals, not the entry of the tunnel, because 3,000 or 4,000 meters there will be nobody, but where the custom and everything is installed, which is maybe something like 10 kilometers away from the entrance. And so we should probably think of a bigger place, maybe on the Chilean side, which is the one which has fast access to the lab.
Right. Yeah, the whole area. I mean, if you let me see if I go back here. Here, so well, these are the entrances of the tunnel, but you will have some, like international police or something, around 10 kilometers away from the tunnel itself, and the whole area here will be international territory. So probably around there, from there to here, will be like 10 kilometers also. Yeah.
So 10 kilometers is way better than doing.
Sure. Yes. Okay.
Yeah, but I think they want the mic because it's also
is there any information the quality of the rock? I'm thinking on the content in uranium, thorium, regarding the, for example, what we can expect for the radon inside.
There were some samples at not at really at the depth of the rock, but this is like 600 meters down or something, right? We're taking a few years ago. There you see the type of rock and the content of uranium, thorium, and potassium. So it's average.
Okay.
Yeah, so this is just 600 because these are the deepest samples that they have now. And we were mostly worried about rhyolite, which, as far as I understood, depending on how it is produced, how it is formed, can have very high flotation. There is a geophysicist here, so I'm not going to talk too much about that. But so we were extremely worried about rhyolite potassium content, and the two samples we had were quite low. But we won't know for sure until they build the first tunnel, which is an activation tunnel, and then we will know. And actually, also the location, the exact location of the lab might change depending on the condition of the rock, if the rock stability they find when they make these tunnels. So we'll have to see at that point. It looks okay.
It looks okay. Yeah. And so I'm thinking about the, for example, the in Modan, the environment is very dry, and in Gran Sasso there is water getting into the inside the rock.
Yes.
Do you have any idea of what will be the situation here? Like
no, we don't know.
Like dry or more like?
Yeah, we actually don't know. That's something we had to see when we get there. What was the situation? Yes, the proposal of Lombardi is that the walls of the laboratory will not be waterproof. I mean, but the design has to be such a way that you don't have drops falling. Everything has to just run on the walls, and then you run them down on the side. So that's mainly what they expect. Of course, we don't know how much water we can find there. And then the temperature, they expect temperatures of 50 to 60 degrees or something like that. Somebody told me at that depth you will have 100 degrees, boiling water. Well, I don't know, but what do you think? Nobody knows. Yes.
Well, it's more similar to Modan than Gran Sasso. It's a bit deeper. The rock is kind of similar also. The length of the tunnel, I mean, it's quite similar. So the 50-ish degrees is what you expect if you don't have a tunnel, right? But But once you have the tunnel, especially since there is this 3-degree slope, and it will be used as a natural ventilation for the tunnel, then the temperature in the tunnel should not be, but it should be 30 something. Half of the power is foreseen for just for the cooling and ventilation of the lab, which is typical numbers. I mean, in Snow Lab, it's 40 something-ish when you walk in the mine. So it's not the best situation in the world, but people are used to it.
Okay. Right.
Okay, so let's thank Claudio again. So now Osvaldo is going to tell us about the physics we are planning to have in Andes.
¿Cómo se pone esto? Al otro lado. Ahí. Así. Esto va ahí y eso va allá. No va a apoyar la cabeza. Por ahí, sí.
Ok, ¿se escucha o no? Qué sé yo, si no le ponemos...
Párate derechito,
Ahí.
Así creo que.
Perfecto, queda bonito. Muy bien. Entonces, veamos. Talk 1. View. Full screen. Presentation. Full screen mode o presentation. Full screen. ¿Qué pusiste? Ah, ok, listo. Perfect. Okay, so as Claudio mentioned already, so the main purpose of the talk is just to introduce the physics that one may perform at Andes, with the intention of having this first proposal for what will be the white paper of the laboratory. So, I mean, so the shopping list is quite long, but the key word there are two. One is neutrinos, and the other is essentially the dark matter. So with the neutrino puzzle, we have the opening for new physics. I mean, the new physics means the possibility to illuminate the sector of the electroweak interaction, which is still unknown. So the neutrino is a massive particle, we know that, because of the oscillation experiments. But we still do not know the either the mass scheme for the mass hierarchy. We don't know either the absolute value of the neutrino mass, and we don't know how the mass of the neutrino is generated. Certainly not by the Higgs mechanism. So 3 problems: how the neutrinos arrange themselves in the hierarchical array of masses, what is the absolute mass of the neutrinos, and how the mass of the neutrinos is generated. And thus conveys us to the second point, which is dark matter. I mean, if whatever the dark matter of the universe is really made up of the right-handed neutrinos. Because if the neutrino is massive, as I'm going to explain, there should be a second generation of, in the sector of the electroweak interaction, that has to do with the right-handed sector. Therefore, should be, I mean, the W right, zeta right, and right neutrinos. So all of them is just going by this wonderful thing which we call neutrino physics. So the subjects are, as I have written there, going from the experiments which are being performed actually, the 2 neutrino double beta decay, which has been measured, the neutrino-less double beta decay, which is still to be measured, so to say, and then the other things like the constraints on the neutrino mass, detections of supernova neutrinos, and new phenomena which are extremely interesting and telling us that the neutrino is a really beautiful and complex particle. Like, I mean, the interaction of neutrinos in the source when they are produced in supernova, neutrino-neutrino interactions, and when they travel along the universe, and they suffer the coherence in the way from the source to the detectors. So all the things, if you think I'm a kind of neutrino fanatic, and you don't believe me that, for the emphasis, then go to the latest report by the NUPEC, and then you will see NUPEC is asking interesting questions. I mean, how the matter on the universe is formed. That is nucleosynthesis. Has to do with neutrinos. Then, what is the composition of dark matter? Again, could be neutrinos. The neutrino physics is just giving you signals of the violation of fundamental symmetries. So the lepton-baryon symmetry is a really sacred law. Lepton flavor violation is present, not to mention the extensions of the standard model. So we really know the standard model is really in a bad shape now. I mean, the standard model of the electroweak interaction, not the standard model of the of quark and gluons. And then all of them drive the attention to the laboratory, which is in this case not undefined by the atomic nucleus. I mean, the laboratory where all these processes can be detected. And as you already know, I mean, that requires conditions which are extremely sensitive to the number of events that one is going to register. And for this we need, I mean, the laboratories, the underground laboratories, the underground physics. So this is a short view of neutrinos. Neutrinos are coming as a linear combination of mass eigenstates. They are very light particles. Therefore, the energy is practically the momentum, and this is why they are very effective in cooling the stars. Small of the energy is carried away by the neutrinos. And then, of course, they have the nice phenomena of the conversion. They can be emitted in some certain combination, and then they can be detected in another combination, like here. So they can be electron neutrinos at the source, and they can be detected as other sort of neutrinos in the detectors. And this is called the probability of survival or disappearance of the neutrinos. So that explains, for instance, the so-called solar puzzle, that the neutrinos are emitted from the pp prime reactions, and there is a deficit, was a deficit in the neutrinos, and that, of course, was the first important discovery, that they can be emitted as electron neutrinos and be detected in another combination. These are called neutrino oscillations, and for this, I mean, Koshiba, Davis, and Jacobi anticipated first the experiments, and that goes to the Nobel Prize lately of Kajita and McDonald in 2015. Then some of the current experiments which are somehow trying to illuminate those sectors are actually being performed in laboratories like the Gran Sasso, SNO, or Modan. And of course, Andes will be a nice place to accommodate, I mean, these sort of experiments, I mean, the next generation, eventually. This is a view of SNO that you already know. So here you measure, I mean, the components of the neutrino currents interacting with the deuterons in the air and producing the signals to the which can be related to this mixing matrix, which may be the most expensive matrix in the history of physics, because each of these elements, the obtention of each of these elements means a lot of time, money, and effort, not to speak of the ingenuity of experiments to perform, because it implies, I mean, measuring fluxes of neutrinos coming from reactors, the mixing of neutrinos and antineutrinos, and then combining phases, like Dirac and Majorana phases, in addition to the CP phases which appear in there. Till now, I mean, there is no evidence on CP violation, but one may assume that if there is CP violation, then this matrix will become a complex, and therefore we have to determine these 18 components of this matrix, which is the Ponte-Corbot and so matrix. As I mentioned before, till now the standard model in the minimal symmetry breaking is compatible with 3 generations of masses, which are this one we call M1, M2, and M3, and the flavor neutrinos, or the current neutrinos, are the ones which we call electron neutrinos, mu neutrinos, and tau neutrinos. The composition of each of these neutrinos in terms of mass eigenstate is shown by different colors in the figures. But again, I mean, if we believe that the beautiful picture of a Higgs boson given masses to all the particles we know, then we have to be careful, because the little neutrinos do not have a mass coming from any sort of Higgs or Yukawa coupling. So we leave apart from now the discussion, theoretical discussion from where the mass may be coming, but then we really don't know how they arrange. We know the difference in masses coming from neutrino oscillations in the solar and atmospheric neutrino experiment, what is called the small scale and the large scale, 10 to the minus 5 electron volt square and 10 to the minus 3 electron volt square. These are the best parameters or global fit of the parameter center in the mixing matrix. The sin square theta 1, 2, the sin square theta 2, 3, and the latest one, which is the sin square theta 1, 3. That was the latest elements incorporated to the, integrated to the matrix. And as you see here, the mass differences are that small numbers, but we know differences, no absolute values. There can be also other neutrinos, what we call relics neutrinos from the first processes of formation of matter. So leptons are essential to explain, I mean, the matter evolution from the Big Bang. When we don't know how many neutrinos are there, there could be also esteral neutrinos, which are not participating in the flavor composition of the current neutrinos. And there are several experiments which are pointing out to the need of these additional components. And this is one sample of these experiments where these esteral neutrinos can be have been mentioned in connection with anomalies in the detections of the neutrino fraction properties coming from the different reaction chains, which are shown in the transparencies. And there are data which are in tension, like the ones coming from Carmen, for instance, as compared with the other sort of measurements like LNSD and mini-boom. So there is some tension between the data. This is our actual acknowledgement of the scale, so to say. We can talk of excluding regions coming from the single beta decay, like the end point of the tritium beta decay, which is telling us that there is an upper limit for the mass. But also we have the cosmological results, say, coming from Planck, and Planck is telling us that the sum of the masses without any elements of the mixing matrix, the total sum may be smaller than 0.23 electron volt. So the question is that from 2.3 electron volt to 0.23 electron volt is a factor 10, and it's a very huge factor for that, in the sense that it could tell you that the limit in the tritium beta decay experiment may be due to other effects, which are not essentially related to neutrino. They can be, for instance, our insufficient acknowledgement of the say, atomic effects or solid state effects which are entering the detection of that, because you are just measuring the endpoint of the single beta decay spectrum. So somehow, but it's very interesting that both the cosmological and the single beta decay limits are so different. Because I mean, in cosmology, you say if the sum of the three elements is 0.23, obviously and trivially, at least one of them may be of that order. So if you divide this number by 3, then you get a mass which is the order of 0.07 eV. And if the mass is the order of 0.07 eV, then you better forget about the current estimations of the double beta decay experiments, because it's just too small. You need to go to very delicate experiments. And then the other effect is this, which is very interesting, and somehow was overlooked for quite a time. And now Smirnov and company are producing very nice papers on that, which is the quantum mechanical structure, the coherence. So what is the coherence? It's not dephasing, it's the coherence. Neutrinos are produced in a source, say in a very distant supernova, and they're coming to the detector. In between, there are other particles. For instance, our beloved right-handed neutrinos that we believe are the best candidate for dark matter. These neutrinos will interact with the ones coming from the source. And they will produce, I mean, what is called decoherence. I mean, they are coming as a pure state in the source, and you get as pointer states, non-pure states, mixed states in the detectors. So therefore, if you are fitting the matrix elements and the mixing of the mixing matrix elements, the composition, by looking at the detection, then they will be missing a very important effect, because they can be telling you something very wrong. And one has to be careful on that. This is how the neutrinos fluxes in a core collapse supernova looks like. And this has been calculated as a function of the different flavor compositions. So the signals are quite different. So therefore, you know how important it is to have in the laboratory some equipment which may detect neutrinos. Remember, the neutrinos are not trapped in either a supernova or in a black hole collapsing scenarios like the photons or ultra high energy gamma rays. They are coming with a delay respect to the neutrinos. So if you really, of course, you take something bright in there, then you may be able to correlate the signal of this gamma ray, high energy gamma rays with the neutrinos. Unfortunately, in the latest events, the neutrinos detectors were not ready to do that. Not in the supernova 1987-8, not in the latest bursts of gamma rays. The neutrinos were missed. But a few milliseconds after the collapse of the neutron stars, or the formation of the black hole, they will be coming, the gamma rays, they will be delayed by the layer of material collapsing to the center, and the neutrinos will pass through that. So it's a very, very interesting scenario. So several open questions. So is lepton number not conserved? Well, if you detect neutrinos double beta decay, the answer will be yes, lepton number is not conserved. What are the neutrinos? Are Majorana particles or Dirac particles? So the Dirac particles are essentially different from the anti-particles. The Majorana particles are totally equal to the anti-particles because they are a linear combination of them. So the light-heavy mass ratio in the seesaw mechanism is the only mechanism possible to explain for the absolute scale of the neutrino mass. And then the absolute scale, from where can we determine that? You say, yes, well, double beta decay experiments will tell you something about that. But what is about the mass hierarchy? For this, you have to resort to cosmology also, I mean, to combine data coming from beta decay and supernovas and so to really to determine the mass hierarchy. Well, and then you can be more sophisticated and ask about CP violation, and then go to some other extensions of the standard model, like, I mean, try to accommodate now a right-handed sector in the theory. And of course, again, coming back to the old problems in neutrino physics, is there any majoron around? Any boson that may be coupled to the neutrinos to give them masses? So you see, if you really get a positive answer to any of these questions, you will go to Stockholm. No? Nuclear double beta decay. In the process which is not telling you anything about the neutrinos, but is telling you about the nuclear structure, you have two neutrons. The energy difference between the initial double even nucleus and the final nucleus is such that you do not have a single beta decay. So it's forbidden by Q-value arguments. So you have to go by virtual transitions. And this is the only process in nature which I know where the leading process is a second order in the electroweak interaction. And then what happened, two neutrinos are produced and two electrons are produced, then you don't know anything about the neutrinos. But the interesting part is this one here. So if you think of a Majorana neutrino, the first nucleon will decay, neutron to proton, will emit a W boson, which will decay to electron and a Majorana neutrino. And this neutrino here, which is emitted as neutrino, must be absorbed as an antineutrino on the other vertex. And this is forbidden by a Dirac neutrino, but it's allowed for a Majorana neutrino. Then you can connect this vertex with the other one here and get here the Majorana neutrinos propagating the momentum from here to there, produce a second decay. This is called neutrinoless double beta decay. You detect the two electrons. Here you have a continuum for the for the spectrum of the two electrons, kind of bell shape. But here you have a single signal, exactly at the Q value of this. If this event is produced, the ratio between this and that is about 1 in 100,000. So actually now the colleagues from the experimental side are telling us that they are so confident that the two neutrino has a half-life of 10 to the 19 to 10 to the 20 years, is now a sort of noise background for the other thing, where the limit for this is 10 to 25 years. You see how fantastic things you are talking about. Measuring the lab half-life of the order of 10 to 25 years, which means in practical sense for the experimentalists, less than one event per gram per year. So then you know why Andes is necessary. Because you have to tell noise from signal with that fantastic tiny number of accounts. And the other thing is, there are experiments, wonderful experiments like Quore, Pia will speak about that probably, where you can really tell the signal, which is really fantastic, even if you have only one event. Because that energy coming from the Q value here, which is the order of 1.5 MeV, will be deposited in the detector and will break the superfluidity, the superconductivity of the animal which has been in this cryogenic regime. And this is different from the other idea, where the detector and the material which decay is the same, like placing huge quantities, say, of germanium and then measuring the signal coming from there. Well, now this is another thing which is pion physics, is producing the same effect, double beta decay. You can connect this one and this one to learn more about the nuclear structure. But also you can do reactions, like double charge chain reactions. Now there is a nice project called Numen, where, you are just doing these double charge chain reactions on nuclei, which are candidates for these double beta decays. Then you can really illuminate not the operators, but the wave functions. So this is my contention to Numen. Numen is not telling you how good or how bad are your theories in calculating the thing for the neutrino double beta decay, but rather it's telling you how good or bad you are in reproducing nuclear wave function for the initial and final state. It's very important information. Well, this is how a theoretician looks at the matrix elements, processes for the double beta decay with two neutrinos. This is allowed by all theories, but has a funny property, is that the matrix elements are extremely small, very tiny matrix elements. So therefore your theory has to be very sensitive to that. And we have reached the point where our nuclear wave functions are able to reproduce the thing. So that gives us confidence on the neutrino-less double beta decay project. When I'm talking of this, you may say, well, this guy is talking about theory. Who cares about theory? Because if you measure something, it's okay. Well, I want to drive your attention. Even if you measure the neutrino-less double beta decay, you will not be able to determine the mechanism, because the theory is still not complete. So you got the point, no? This is why, and if you want to design an experiment for neutrino-less double beta decay, you should know the theoretical numbers, because that gives you an idea of the amount of material, amount of money that you will have to design the experiment. So it's one very challenging field where theory and experiments are like a normal marriage situation. It's a marriage by compromise, no? So one is getting something from the other, and both are happy. There is a peculiar behavior in the, I will go very fast to that, on the double beta decay, the allowed double beta decay to neutrino mode, which is that it's not any, there is nothing like a universal feature on that. You have to go case by case. This is why it's so important to collect the information for all the current experiments. So years ago, there was a discussion in the NUPEC saying, well, we cannot afford to have so many different experiments for that. Let's have only one experiment for that, or two experiments, because we're talking of how much? 140 million euros for each one. About, in the material, no? About. So, but the question, if you have only one experiment, so you will never tell us that you have sensitivity enough to believe that you are really on the good track concerning the other. I mean, there's so much. So therefore, they don't have to make a decision to which kind of experiment can be performed on that. For in the case of Andes, so what I'm going to propose is tellurium 128 and tellurium 130. It's a nice candidate, has not been measured in other places. I mean, they're very tiny samples in NEMO for that, but perhaps can be our flag experiment for double beta decay. It's not so expensive, tellurium, like would be germanium or calcium or the other, or molybdenum. So it's a good candidate to think about. And even more, for tellurium, we can do other type of experiment, like using beams of tritons in the accelerators in Buenos Aires, tandem, or deuterons, either here or in Buenos Aires, to do a spectroscopic analysis of the transitions around the initial and final states of tellurium. This is a compilation of the half-life for the allowed decay done by Sasha Barabas. And you see the spreading is between 10 to the 19, 10 to the 21 years. This is for the allowed decay. And the longest one, the most difficult to measure is the double electron capture, but also there are some geochemical experiments. Well, what about the most interesting one, the neutrino double beta decay? Here, the half-life is depending on three factors: phase pi factor, nuclear matrix elements, and neutrino masses. So three elements which are coming together to give you the half-life. So till now, you measure the non-observation of it. That means you put the limit of this, because you have not seen the decay. So therefore, if you fix, they have the phase pi factor, and you have control on the matrix element, you may be able to extract the neutrino masses. This is not quite, the matrix elements in different theories are somehow spreading around, but the overall nuclear matrix elements are known, are that much. This is an idea how they spread for different theories and different nucleus. But what about the phase pi factors? So to our misery, we found that the GA factor, the axial vector coupling constant, apparently looks different for the single beta decay and for double beta decay. That means either we are wrong in writing the elementary theory of the interactions, or there is something we still don't know on the reaction, on the interaction mechanism, which is controlling the decay. So realist physics at the very, very, very frontiers. this is the situation exploring the mass hierarchy. These plots are coming from Kamlan. And then you see that if the neutrinos are living in the so-called normal hierarchy, the situation for double beta decay experiment will be very, very difficult because the mass splitting will be very, very small. What about going to LHC? Because at the end, so if you are comparing reactions with transitions, so measuring transitions, which are extremely rare, is very difficult. But doing reactions at high energy may be much easier. Now, in CERN, in the Large Hadron Collider, they have some lines which are dedicated to the measurements of the jets and two leptons coming out of the proton collisions. So the experiment is called CMS. And CMS is telling you that practically this, that you have the collision here is a virtual boson being excited, and then you produce, two leptons and jets, provided there is not only a virtual boson, which should be a right-handed boson, but also right-handed neutrinos. If you compare this diagram with this one here, this is our below double beta decay without neutrinos. It's the same. With the exception that you are replacing a light mass Majorana neutrino for a heavy right-handed neutrino there. So it could be that you can connect the cross-section of this reaction with the matrix element of this transition. And this is done. These are the numbers which are coming from Gerda and Kamlan-Sen, which are the world leaders in the neutrinos double beta decay. By taking out the limits of the neutrino mass, the effective neutrino mass coming from double beta decay, and extracting the parameters of the electroweak Hamiltonian that has right-handed and left-handed and left to right-handed interactions. The complete Hamiltonian, and then this is what is coming out. So these are the two lines which are constructed with the result from Kamlan and Gerda, and these are compatible with their limits for the light neutrinos. Here is the mixing angle between the would-be right-handed bosons if they exist. These are the limits of the mixing angle excluded by twist. These are the region. This is the region allowed by CMS and double beta decay, and these are the allowed masses for this animal. That means if you believe that these limits are good and that nature is somehow good to you, so that the neutrino mass may be around that value, say 0.1 eV or 0.07 EV, then you are telling us that they should be right-handed neutrinos at about, say, 2.5 or 3 tera-electron volts. And this is really new physics. You are discovering now new elements. And this will complete your theory. So then you can combine high energy data from double beta decay. And this is supporting our claim that we need to do more on these double beta decay experiments, because they can really be complementary to the reactor physics. So that means there is compatibility between the neutrino mass limits coming from double beta decay and the neutrino mass limits coming from the reaction theories. Okay, the future of experiments. Well, there are several. SuperNeMo is one of them. and it's interesting for Andes because they this is an experiment with maybe fragmented in modules. So SuperNeMo or NeMo is having not one element but several elements which are acting as sources, and they're making sort of average on the Q values, and then from that getting a sort of average on the measurement. So, and they're already working as experiments, so the R&D was already done. So that means as a starting point, it should be nice to have one of these modules in Andes. But then what makes our life very interesting from the point of view of Andes is that those experiments, when performed at a large scale, do not have places to be installed, because no Gran Sasso, no Modan, or SNO can be extended much on their actual size. So then they have a window of opportunity there. Okay, so this is a list of the experiments and the location of them. Both the current and the planet experiments. What about dark matter? Well, we also may dedicate the setups for double beta decay to measure dark matter things. They are completely compatible. You don't have to have new devices. And you can tell from the experiment something very interesting, because in the so how the idea is that the dark matter, so we are moving essentially in dark matter, and so the particles are exchanging momentum. They are not interacting electromagnetically, exchange momentum with the nucleons in the sample, and so we measure the recoil energy coming from the nucleons. So this is the sort of experiments that, and of course, since we are moving in orbits and the sun is moving also in orbits, there should be modulations according to the time during the day, the time during the year, where we may move in favor or against the flux of this background of dark matter. There are several experiments like DAMA, CRES, COGEN, CDMS, Xenon, SABRE, NIMES, ICE, and they point out to this sort of scheme. Here I assume there is a weakly interacting massive particles, is coming near a nucleus, producing the momentum transfer. There is a recoil, the wind is going by, and then you measure this. And the modulation has to do essentially with the fact that we are moving in orbits. Then you can express the recoil rate in terms of known factors like the distribution of the velocities of the dark matter candidates in the universe and the cross sections for the transfer that you have. And what is interesting that also you may correlate the signals with the actual position of the laboratories. And here I have taken as a comparison Gran Sasso and Soudan, Andes. This is the Australian laboratory, and this is IceCube in the South Pole. And you may relate now the cross sections as a function, both the annual and diurnal modulations, by using this information about the position of, say, of the detectors. And then if you compare, for instance, the signal in Sudan with the signal in Andes, they will be different, the maximum of the signal. So for Andes, maybe an amplification of the signal with respect to that. Assuming, like in the previous case, that the WIMP has a mass of 10 JeV, and that the cross-section in the spin-independent mode is about 2.10 to the -15 femtometer square. And the same happened with the diurnal modulation. There is a shift. So that means that you can talk of a kind of a, it's not a correlation, but I mean, if you have a signal in the northern hemisphere, and you have a signal in the southern one, you may really confront one signal with the other and get this sort of information. It's also dependent on the detector, and again I have here calculated this for Andes, assuming the experimentalists are using germanium detectors and integrating the signal. So then at the end we may conclude that the experiments in both in dark matter than with sodium iodine detectors and germanium is better in the germanium than the sodium iodine. So they may tell you, I mean, something very definite about the signal, where the signal is really produced by a WIMP or not. Well, then at the end, along the line of what Claudio said before, so we shall discuss on that more tomorrow. These are things how that may be in the white paper of Andes. So a definite proposal for double beta decay. What I'm proposing here is an experiment based on tellurium. Then a proposal for the dark matter detector, sort of DAMA kind of experimental array. And then, as we're going to discuss tomorrow, I mean, the activities on Andes will not be only centered on physics. But of course, I mean, you have several other applications in biology, seismology, and detector technology. So that Andes is really a unique opportunity to do these exciting things. But you see that what I like to stress that after going on all this point is that Andes should not be a repository. What I mean by repository, simply just a place hole where I go, put my detectors, take my measurements, and go away. This is absolutely useless. Okay, so Andes should have a flag experiment, should have a definite research line, should have a supporting academic institution around, and should be really a factory for human resources in the area. So that's all, and I hope you will enjoy more during the workshop of this very nice physics, which is coming by a very tiny particle. By the way, neutrino, like most of the good thing in physics, is coming from an Italian word. Thank you very much.
You mentioned that a good candidate for neutrinoless beta decay experiment would be tellurium isotope. Do you know how easy it is to get it produced, to get hold of, to buy it basically? Because SuperNeMo opted for mainly selenium, and I think one of the main reasons is the ease to get it compared to other isotopes.
if I may add to the clarification, yeah, so tellurium is the only isotope that does not need to be enriched. So that's why it's much cheaper. Natural tellurium has about 80% of tellurium-130, which is the double beta emitter, while all the others need to be enriched, and that makes much more expensive. Now, so that's the advantage. Now, the disadvantage is that tellurium, well, as it made in Quore, tellurium, it's not scintillating, so it's more difficult to discriminate the background.
This is more of a comment. You said that the dark matter experiment and neutrino-less double beta decay experiment can coincide to one experiment. Yeah, I mean, I just want to comment. It would be very hard to build something that would be both sensitive for KV's recoil energy and for MEV's. I know for xenon, background is very dominated in high. I mean, for us at MEVs, we have quite a lot of background, so we are completely insensitive for neutrino-less double beta decay. We can do these searches, but we will not be compatible with EXO or NEXTO, for example.
Sure,
so, and vice versa, of course.
The idea of the comment was that if you, I mean, step number one, you should have to have the material. And suppose you get enough, say, tellurium to produce, to have, I mean, the double beta decay space. Then with the same tellurium, you can perform a dark matter.
Yeah, but
so you don't have to produce more material. That's the point.
Yeah, I'm just.
You may refine the detector, but not the material.
Yeah, okay, exactly. So yes, that was just the comment. Yeah.
Okay. Because actually, the same sort of analysis the one that is going to perform. I mean, so the same. So all the theories is practically expressed in the same way. Eh? No, the experiments are.
You can use the material, but you need to build a different apparatus.
No, I know that. So, and also when I didn't mention that, but I mean, the results which have been produced by both Gerda and Kamlan are really fantastic. I mean, but they're based. One is based on the good reproduction of the background, which is the critical point. So you really can calculate till the very tiny quantity, the amount of background you have, then you are sure in the analysis you are performing of the scene. So this is the main point of these two experiments. While in the others, I mean, you really have difficulty. So this is why I like, I mean, as I told Pia the other day, I mean, there are two lines. Either you are very big because you have a lot of material, but I mean, you cannot remove the material to measure the background because your detector is the material which is decaying. And this is very difficult, like genius, supergenius, and those things. While the other one, the cryogenic, are really better things because they're not only smaller, but I mean, you really can control the vacuum completely. I mean, so all these materials which are decaying by double beta decay are also superconductive in the metallic regime. So the idea is that if you really produce the decay in these wires, then you convert, I mean, the signal into heat and then you break, I mean, the event, and you know precisely that you are at the Q value. So I have seen remember the first simulation done by Fiorini. He was so happy about getting, I mean, the curves there was Cuoricino, no? Cuoricino. And really it was very, very, very well fine-tuned. So the other thing is about tellurium, which is also good for the theoretical point of view, that, I mean, the Q value is not that small. Because when the Q value is about, say, 1 MeV, you have a lot of contamination coming from other transitions. So, and this is a little larger, one of the largest ones. And the structure is much easier to calculate. And in addition to that, like you can do experiments like the one that Sean Schiffer performed on germanium by doing particle transfer reaction on both the initial and final state of the system. So it's just to get, I mean, the control on the initial and final wave frames. So in Tellurium you can do the same. So this is why it is my proposal for kind of flag experiment in the region based on Tellurium. Something good.
Okay, so let's thank Osvaldo again.
Thank you to you.
Yes. So now we are moving from our usual high energy physics field to geoscience. So
Is there any experimentalist in the room?
Yeah. Let us just copy this. So here is another one.
it should have the same name as the other. We brought some.
And then it's down here. So going from a Mac to a Windows machine without glasses is not very easy. Okay, so what I want to show in the next 15-20 minutes is the approach we are going to take to try to establish an Andes Geo Consortium. So how can we do some geoscience experiments using the newly or being newly established Andes laboratory? And I came to the whole project last year, and it really started there that we were trying to put things together. What I want to show you first is a simple outline. So I will talk a little bit about the seismicity in the region, not very much, but I think it is one of these things you're going to build this in the Andes, which really means there will be big earthquakes. And if you're talking about a lifetime of 30 to 40 years, there will be at least one incident where you might have to switch off some of your experiments during that time. So you really have to take this into your design considerations when you're doing this. I don't want to scare you because I think it's a brilliant idea to actually work in that region, but you should not ignore it. Then I will show you a little bit what we have in southern Germany, a Black Forest Observatory, which is an underground observatory for seismology. Then some ideas how we want to do geoscientific and material science work in such a laboratory, and some scope and current activities. So that is historical seismicity and observed seismicity along the South American margin. We are about 30 degrees, so really in the bottom area. And the numbers here, the years are 1943, 2004, 2006. These are significant magnitude 8 earthquakes. So you will feel some of the shaking, at least your experiments, your instruments will feel some of it. So I think we are far enough away from the whole thing, but you have to really design and build and do your experiments in such a way. And the South American margin, if you go further to the south, it's also the 1960 Valdivia earthquake, which was the greatest instrumentally recorded earthquake ever. What makes it a very, very interesting site for us as well is something what we call a flat subduction. So simple saying is we have on the west, we have the Nazca Plate with the Pacific Ocean. The Nazca Plate is going beneath South America, And you can see this very nicely here in the lower cross-section S3. So the downgoing plate is here depicted with the seismicity, with the earthquakes which are happening in a depth range between up to 200 kilometers. But then when we come to the segment around 30 degrees, you can clearly see that the slab is not going down anymore, it's going into a plateau. And what is also has a consequence of this is that actually you don't have any active volcanoes right now in this region, which is good, because otherwise it would be even warmer at this depth range. For us, it's very interesting because we don't understand how actually this slab movement, what controls a flat slab. That's for us a very unknown feature right now, and we would be sitting with our instruments directly on top of it, and of course such an observatory would also have its own seismological networks integrated with the Chilean and the Argentinian network, so we could look at it. But what you can also see is there are earthquakes all the time in this region, which you can instrumentally record. So you really have to then specify what is the shaking at your base of your instrument and what do you have to do, what can you still tolerate. But you can measure it and we can actually help with it quite easily. That is just depicted a little bit better. So we have the normal slab subduction, we have the flat slab subduction, and we know more or less quite well in the region where it happens, what is the seismicity rate, what is the background rate, what on average can you expect. There was a larger earthquake in 2015, the Illapel earthquake, more or less directly in front of this Agua Negra tunnel, and we have now enough instrumentally recorded earthquakes in the region to actually do some proper shaking predictions for such a site. So this information is there. I just want to flag it that this should be a consideration. Let's go to a more conceptual model for seismologists. How do we depict that actually when one plate is going down beneath another plate, how is the movement happening at this interface? Of course, it would be very nice to write down in the white paper that with this Agua Negra or with the Andes lab we can predict earthquakes. No, we will not reach that. That would be really a nice thing to do, but no, we cannot do that. But we can better monitor and look at the processes which are happening at this area where the two plates are clamping together. And it's not only that these plates are releasing their energy due to big earthquakes, there are a lot of different processes going on. Sometimes it's stable sliding, sometimes it's clamping, and then you have big earthquakes. Sometimes an earthquake happens during 2 weeks. You will not feel it, but you can measure the displacement of it. And we have a better idea how this is structured now in depth, but with such an observatory where we are really sitting on top of the slab at 100-kilometer depth, that would be an ideal place to do. I told you just before, there are earthquakes which are called slow earthquakes. They are happening about in a time frame of 2 weeks, not 2 minutes or 60 seconds like a normal large earthquake does. And this is here depicted and shown with this GPS data. So it's the east component, and you can see every 15 months actually the North American plate moves a little bit to the west. You will not feel it, you cannot record it with seismometers, but it does it every 15 months. And in the beginning, people who are working with the GPS data thought there's some error in their detectors, unless they found it then in many GPS stations, and then they had a lot of nature and science papers out which were describing this, and now it's found at every subduction zone. For Chile, we haven't seen such a behavior yet. it would be interesting to see what is happening in this area of flat slab subduction. The other thing is when you're deeper in the mountain, your noise levels are going down. I will show this. And what we want to do also is detecting rupture fronts. How actually is the earthquake source breaking, and how can we see this process happening? This is just a rupture front here, and the amount of slip then determined out of it. And if you have a magnitude 8 earthquakes, the actual displacement at the fault is about 6 to 8 to 10 meters. And we want to see how fast is actually the rock or the two plates moving along during an earthquake. So that is just the science setting for the Andes lab. Now, what can we do in geophysics and in seismology in an underground laboratory? So here is the Black Forest Observatory, BFO, it is known for. We have here southern Germany, here's France. This is the Rheingraben, this is the Black Forest, and really in the middle here we have this observatory. And how does it look like? That's something like a floor plan. It's an old mine, which was used to actually get iron ore out, and it was built about 200 years ago, and then it was used for geophysics about 50 years ago. There was a little bit more money put into it so that it is stable and that you can do something. The overburden is only 170 meters. You have here your lab building at an altitude of 580 meters, and then you have this complicated system of old tunnels in there which were used for mining. And I can show some of some inside pictures will come. So you cannot go in as tall as I am. You have to a little bit lean over because it's not high enough. And it's also very narrow. It's about 1.50 meters. So it's not ideal for installing instruments, but it was just there, and therefore it was very cheap to use it. And then there are rooms in there where even some of my researchers have never been in there. The instruments were there installed 20 years, and we really don't want to touch them. As long as they are running, as long as the data is coming out, we don't want to do anything to them, because when you are going into the room, you bring cold air in, you get convection, you get all of this. You want to have them completely stable temperature without any noise surrounding it. And observables are acceleration, tilt, strain, gravity, magnetic field, GPS position, ambient pressure, and a lot more. What can we do with some of these? So this is just a picture from the eigenmodes of the Earth. So if a magnitude 9 earthquake, the Tohoku-Oki earthquake, for example, is happening, then the Earth is ringing like a bell. And you can not only determine then the 1D structure of this bell, you can even determine the 3D structure of this bell, but you have to determine all these spectral peaks with very high precision, and you need a very good instrument for this and very stable recording conditions. Then we have something which is called the low noise model. So how good can we get to install our instruments so that no other physical process like wind, like people walking around, like any influences from the recorders, and you go here from 10 seconds to 1,000 seconds to 1 million seconds, and you can see how actually the noise floor is changing. And Black Forest Observatory is really defining, for example, here for the horizontal components, this low noise model. You can't measure it anywhere better right now than in that area. So to have more instruments of this quality in the southern hemisphere, would really help to constrain better on the long period side our models. The problem we have, and I don't want to evade it, is at the high frequency side, the traffic tunnel will make a problem. And that is why we want to be as far as possible from the tunnel away, where you have traffics. And we even have seen, for example, in some of the experiments in the Alps, taking out the gullies around the observatory. So where the big cars are always going into the gully, they sealed it in that area, really made the data much better. So there are some consideration we can do, but it's not ideal. But this is only affecting the high frequency part. When we are going into the low frequency part, some other effects might be interesting. Here's just the spectrum now in periods. What are the processes we can look at? Here in this area, it will be really interesting where we are sitting for these slow and silent earthquakes, where you have an earthquake which lasts about 2 weeks. The 2 lines here is a seismometer with its performance. This is a gravimeter, and we want to install a gravimeter as well in that area. And if we can go up to these, go a little bit lower, we can even look at the secular deformations of the Earth. How does it change slowly? So, superconducting gravimeter, how can we measure very, very precisely the Earth's acceleration? And we have one here, and that is also shown a little bit to get an idea how these instrument caves should look like. Here, everything is open, so the walls are not covered, which is good for us because we can see, are there fractures in there? Where is the fluid coming out? Where there are some different veins of quartz going through, which might decouple the 2 sides. But the whole thing is also wet. It is dripping, and we have a tilt of about 1 degree to get the water out. Because we don't want to have any ventilation and any active other devices to change the rock mass. Even by installing now these experiments here, because this is all, we have to cool down the helium, we are increasing the temperature over long time in this room. And we will see it. At one stage, we will see it. So that is really something we always have to think, how can we make this environment stable? How precise these things are is, and I was completely amazed when I took over the job, they allowed me that we go in. So we went in with 5 persons, and this is the output of the Earth's acceleration. And this is the gravity effect of 5 people standing very close to the gravimeter and actually pulling the mass up. So that is how precise these things are. So we were talking about it when we then saw these big caverns. 30 meters high, circle of 15 meters. How much mass will go in there? When will we start to actually see it on our instruments that you are changing the mass in that area? So these effects we can have crosstalk. That's all I'm saying. So it's interesting. I think it's a great experiment, but we are in that realm. Where are these superconducting gravimeters installed? Of course, most of them are in Europe. Then there was one in Concepcion for 10 years' time. It's currently in La Plata. So having one really now in the center of the Andes, we could even start doing relative measurements. And from colleagues of mine, they had a very interesting paper to use actually gravity signal also for early warning purposes. Because if the earthquake happens, the rearranging of the mass will happen instantaneously, after the rupture has stopped. So if you can measure it, then you could actually estimate how big the earthquake was even before the wave has arrived, the seismic wave has arrived at your place. So there are some ideas floating around now where you can use these very detailed and very high precision measurements. So how good some of these seismometers are is signal amplitudes of 10 parts per the million second minus squared, 1 over second squared, can be measured. If you just translate this in a little bit of a numbers game, so if you use the biggest US aircraft carrier, put a little string here at the top to your record player, and you put the needle down. So the acceleration that this aircraft carrier is feeling would be about 10 to the minus 12. So that is in the area we are trying to measure, and which can be shown that we actually can do it. Now I come to one area which is the GeoMat lab. So this is mainly promoted by Uli Glasmacher. So what he's saying is that crystallization of amorphous thin films without cosmic irradiation. So it's really, we can do experiments that currently are being done in space under a lot of radiation. We can do the counterpart now in an underground lab without any radiation, or with a very reduced amount of radiation, to really find out what are some of the controlling processes which can be interesting. So long-term monitoring of geogenic gases. So there we would need the rock phase. What is really coming out of the origin? Does it change after a large earthquake? Does it change before a large earthquake? Are there any processes where you can sample directly in such a mountain chain? Long-term monitoring of magnetic susceptibility, rheological and geochemical investigations. So more on the material sciences. Here are two phosphoryte films, just one or two layers of elements. And one was only stored for 8 hours, and you have perfect crystallization afterwards. The other one was stored for several months, and you just see very, 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 very small crystals in there. And they did a lot of experiments to rule out some of the other components, but maybe the crystallization structure of the same material is extremely sensitive to the formation of crystal seeds, yes? And crystal seeds are related to natural high energy radiation. So if you have the film only prepared for 8 hours, yes, you only have a few seeds. If you let it sit there for a long time, you will have many, many, many seeds, so only very, very small crystals. So these kind of ideas, they are currently talking about what kind of experiments can you do underground, which actually could have some consequences. And if you have such a laboratory, and I think especially for South America, you can test your own instruments. You can actually kickstart some developments, because you would have a baseline observatory where you know what can you record, what can't you record, what comes from the Earth, what comes from the instrument. So, what are scope of the Andes GeoLab? So long-term observation of geophysical parameters. This is deformation, and there we go from static to high frequency, so the full spectrum. Earthquake rupture process, and establish a reference observatory for seismology in South America. That would be more or less the scope from that side. Long-term observation in gas fluid chemistry, including isotopes. So this is a very hot topic right now. Everything in earth sciences is currently fluid or volatile related. A lot of the processes we are talking about have fluids involved. And we can sample them directly now. processes of mineral deposition. So how is Chuquicamata come about? What are the processes behind it that actually make ore enrichment in the Andes, or have been made? Changes to fluid and gas flux, and then on the more material sciences are crystallization processes and comparison with experiments under the influence of cosmic rays. So that was my idea about 9 months ago. That was the first design of the Andes lab, and I just put this green line in here and said that should be the Andes GeoLab. There's a geophysical extension to it. And then we were sitting again and again together with our experience we have from the Black Forest Observatory, and we came up with this proposal where we have something like an entrance here. We have all these airlocks because we really found out that barometric changes are changing the observable. So you really have to keep the barometric changes out. And we have strain meters here. We have some instruments in here, broadband instruments, but we also want to have cavities here where people can come in and do guest experiments. For a year, for 2 years, they have designed a new instrument and they want to test it. Best thing what is happening right now in the area of seismology are ring lasers, where you can measure directly also the rotation of the Earth. Or in the long run, it might be very useful to have here a permanent ring laser which can actually measure the changes of the length in day directly. It's really something which is becoming a very hot topic and which can revolutionize part of the things we are doing. So we want to be a little bit flexible on that side to have space other than permanent monitoring for the next 10, 15, 20 years. This Claudio already has shown. So here is now the mainly physics lab, and then this would be the extension. And I just put down what our current plan was and how this translates into the drawings of Lombardy. So we went down to Lucerne to directly talk to them because they don't know what we need as a requirement. So if we are saying, oh, we don't want any cement around it, we all want to have the open rock face, they look at us and saying, you are crazy. No, we can't do that. So we talked to them directly. So our idea in the beginning was that this tunnel here, it's only 2 meters wide, 2.50 meters high. They said, yes, you can have this, but then we have to employ 100 persons who are doing this by hand. Oh. Yeah. These are then the discussions you have to start to actually try to find out what is possible and what is not possible. So then we said, what is then the smallest tunnel and diameter you can build where you can still do it with a machine? And then there are these considerations. So in the end, the compromise is we have to make it shorter, because otherwise, if we have the same length, it would be too expensive. Yeah. So this is currently where we are. Then the other thing, what we found out is also they can't do these cavities which are rectangular. It's very, very difficult for them. It's much easier for them to actually have just a tunnel with a rock face. So we are changing now all our designs so to have actually wider cavities with 2 instrument bases where we then put the instruments on, just to use the space better. If you want to have 4 meters, you need a height of 4 meters. Yeah, because otherwise, So when Claudio was showing me and we were discussing also the design of this big cavity here, the roof as it is right now doesn't look right. They say it, well, we have to do something there. it's not a proper arch, so it will be not nice to build. If it doesn't look right, it's very, very, very difficult to do. So we went step by step through all of this, try to somehow keep the volume the same, but compromise how can it be better built. And they have now all the information. It's still a constant discussion. Hopefully they're coming back with some new drawings very quickly. But now they know the specifications. Also, these airlocks, they are homemade built. So we went through 5 different doors of iterations to get them tight. So they know now how it looks like, they have all the information. But I think that is now really the next step, to come up with some solid description for the tender, because everything what is not in the tender will be massively expensive afterwards. So all considerations you have right now, how these things should look like, has to be right now in these tender documentations. And this doesn't mean where the switch is, but this means the basic design. Is there air conditioning in there? How is the water coming out? What kind of things? This has to be defined. And it's not too complicated. So really this 2 hours meeting, 3 hours meeting with them did solve all problems. Except for the money, yes. So, finally, to get more momentum behind it, we could secure some money to actually host a workshop now in San Juan. 14th to 17th of November is now the anticipated date. There should be very quickly now the first curricula, coming out. It's sitting on my desk. I was completely busy. I couldn't work more on it. And with some basic ideas, topics to include. It's really for geoscientists. I want to have it that it is for geoscientists who have worked in the Andes or want to work in the Andes, which is definitely Chile, Argentina, but also Peru, all the other South American countries. But also, I think some of the international players should be there, like groups from the US, group from France. At least invite them all, so that they know this is happening and that we are getting a big consortium behind it. And I am really looking forward to the discussions tomorrow, how you want to do it in the physics community, because I think we can learn still a little bit how these things are set up. But the initial response when we started it was very positive. So I only sent out emails and people were actually starting, oh yeah, how can we help? Can we participate? What are the ideas? What do you want to do? So it was really, I think, a very encouraging step. So right now we have an academic committee here, mainly from Chile, Italy, Argentina, and from Germany. But I think this is mainly right now to get the thing going. The workshop hopefully will get more international players in, and then we see how we can structure it very effectively. So money for this year for a workshop is secured. We have some indications that we can have a second workshop then in 2019 in Chile, in mainly Santiago de Chile, to have this reciprocity in there so that nobody is feeling left out. I must say, talking to you guys in the physics community, you are so far light years ahead of what is happening very often in the earth science community. So there are a lot of more things you have to get people talking to each other, share things. We really have to work on that. I think we can learn a lot from you guys. Thank you.
Questions?
It's a very interesting talk, so I thank you for it. Question about the size. So, if been limited by the size of the instruments, or what? When you say
so
you are limited by the size of the instruments, or
so we are. So first of all, the best thing would be to have a 2-kilometer small tunnel perpendicular to the road tunnel, and then we have the lab there, because what I said is some of the instruments we don't want to touch.
That's okay, but
yeah.
I mean,
yes.
So when you mentioned that in Germany you were moving in a tunnel which was on a mine which was less than 2 meters by 2 meters.
Yeah. But it works. It's okay.
So why you want 4 meters then?
Because they can't build it otherwise.
That's the smallest standard construction.
It is. That's what I said. That's what I said. If we want to have a 2 by 2.5 meter tunnel,
that's okay. Yeah.
Then you have to take a chisel and do it by hand.
Okay. Okay.
Yeah.
The machine has to be able to. Sure. No. But
yeah.
I saw you have a limitation for the size because you can do as well with robots and things like that. If I mean, just to move all the small equipment everywhere.
Yeah, that's okay, but they can't build it.
Mm-hmm. One question. I mean, so because perhaps I lost it during your talk. So what about measuring the energy released during earthquakes? I mean, you have the longitudinal waves and the transverse waves. And
we can't measure the energy directly. That is our problem. We can measure the seismic radiated energy.
Yes.
But we cannot measure what is going into the heat. We cannot measure how much is going into the fracture energy. We can only measure the radiated energy. And that is the easiest thing to do. You just take your velocity trace and square it and sum it up. Roughly speaking, with some factors before.
And then the last question, you were talking about something very interesting, which is the getting the crystallization of some materials underground. That's quite interesting because I mean, if you can do that at somehow a moderate scale or large scale, then a portion of the detectors can be built there.
It's not my.
And then you avoid all this thing of transporting the thing, getting cosmic radiation, having to cut the surface of the detector and so on. So that will really be a breakthrough. I mean, it's very interesting, very good. And what about biology?
I am not the person for biology.
No, but I guess you are bacteria sitting rocks and things like that. I mean, they exist.
They exist. So yeah. But I think. So one of the problems. So if you talk about these things and if it is a completely new tunnel, so what are the problems we can see? Okay, the whole tunnel will be built by explosives. So you will damage the rock, and we don't know how far. So when we talk to them is, okay, at least where we will build the laboratory, there will be explosionary wells horizontally into the rock, and they will all be cored. So we should know very, very soon what kind of material we will find, what can be built, what can't be built, and all of these things. So they know how to do it, and it was really, really good to see that they understand our problems. We also wrote now in the specification for this GeoLab tunnel that there should be smaller charges used, so that the rock is not so much cracked. Yeah, so you can somehow mitigate, but of course, an ore mine which was sitting empty for 100 years has completely been in a stable position. Yeah, so maybe we have to wait for the first 5 years. But even that, I think, is a very good experiment, because we haven't done it before. We don't know what are the healing processes. And if you talk about healing processes, the same then you can apply for large earthquakes. How long does it take for the fractured rock during the earthquake to heal again, to sustain the next level of stress before it ruptures again. So there are more experiments that you can actually do, but some of them you can only write down as some ideas which you have to follow up when you have the real rock in front of you. Otherwise it will be difficult.
In the subduction and rupture process, I don't know if the magnetic field of Earth will change with, I mean, in the earthquake, could the local magnetic field of Earth change?
No,
okay.
No, I don't know. No. So the magnetics. So we were trying to talk to many people. What kind of magnetic experiments could you imagine to do underground? But they were not coming up with a lot of ideas.
So this is a question not directly related to your talk, but I think you'll be able to answer better than the physicists. While you are digging the tunnel, is there any material useful that can be taken out?
Yes. So during the whole excavation phase, there should be, and people are talking about how can we have enough geologists around looking at the rocks which are coming out.
Right.
And especially they will always drill in advance and core. So we have to make sure that actually this material will get into an archive so that it can be studied later on.
So we want, for example, low radiation material, so maybe it's a good place to take that.
Yeah.
Last question, then we finish at the coffee break.
So the processes that you are interested are like 200 kilometers deep in the crust, down, no? More
no, not only. So this is one aspect. So let's go to the first map. I think that is the best to look at. So we are of course interested in what is happening at the plate interface here, what we call the subduction interface, where the two plates are clinging together, which is offshore. And since we are so deep, our detection level should be very good for this. And what I said regarding these gravitational changes, if there will be a big earthquake, that would be an ideal data set. The other process is, it is constantly actually the seismicity is starting from here at the trench where the plate is going down to about 100, 120 kilometers. And the idea for these earthquakes is still hotly debated because it's too warm to have it as a pure stick-slip frictional behavior. There must be more going on. Fluids is currently one of these big words in there.
My question is just to understand for myself. So you want to? It's good for you to be like 2 kilometers down the mountain because it's quiet, but also because the process. So what's the advantage?
So to be in an underground laboratory, the advantage is that the background noise level is much lower.
That's the prime.
That is the prime. That is the prime reason. How deep we have to be for some of these observables, we don't know. If 170 meters would already be enough in Black Forest, it seems to be. But what I think is very exciting, it would be the first time we have geophysical instruments really inside a currently active orogeny, a currently active mountain building area.
Okay, last question from Claudio, and then we go for the coffee. We never have geophysicists in our meetings, so.
Yeah, well, this is a question about like civil engineering, earthquake-proof structures. Yeah. In Chile, they can build buildings who sustain anything. Yeah. But the point is, when you go underground, things are different, I suppose. you have a different spectrum of frequencies or etc.
So it should be better because because the free surface is an amplification roughly of a factor of 2. So you're inside now, but then you have to take into account if you have a big cavity, you have cavity effects then, you have to calculate this. You can do it. So, but the problem is, I think from being with you last year, when I heard, okay, you have these big liquid detectors and you don't want to have any disturbance whatsoever. So if it is a little bit shaking and then your lining or so goes off and then all the little isotopes or material goes into your detector, you then have to wait for another 5 years. So, and I think we have to think about what are the thresholds in acceleration, in velocity, before these effects starts, and how can we mitigate it?
Right.
Yeah, okay. That is, I don't think it is dangerous, no. It is more like the question we had before, what do I do with my experiment? Yeah, what do I do with my experiment to get it? Yeah. Yeah.
So I woke up from the shaking apartment, which is 10 kilometers from the underground lab. But the experiment we saw is sub-millimeter. So yeah, so the experiment was sub-millimeter change.
Yeah.
So really, when you're underground, you're usually in the better.
It is more stable, but this was magnitude 6. You're now talking about magnitude 8, which is, and the problem is that you're exciting more low frequency energy, so the whole thing begins to move at lower frequencies, which then can start some reverberation in your experiments and these things.
I will send the PDF without the Except for the one style. No, I don't have HDMI. Okay. It's a mini display for 2 HDMI. Right. Which I tend to bring with me always, except for the one time that I use it. Right.
Murphy's law.
Exactly. Yeah. Yes, I think I can make this.